Hi everyone. Today we're going to be talking about a new algorithm that we call Sparse Sensor Placement Optimization for classification. My name is Brunton. I'm from the University of Washington, and the other co-authors on this work are Steve Brunton, Josh Proctor, and Nathan Kutz. The basic perspective we're taking in this work is asking the question, given a fixed budget of sensors, where should they be placed to best inform decision making? Now, this is relevant for a variety of engineering and scientific applications. So, for example, we're interested in sensor networks for purposes of surveillance and measurement. In certain cases, you want to either deploy buoys in the ocean or put electrodes in the brain or decide where to vaccinate your population. And you have a fixed number of sensors and measurements you're able to acquire, either for economic reasons, for power reasons, or some other type of reason that can be articulated by a cost function. In those cases, we want to know, to accomplish a specific task that is categorical, where should those sensors be? Similarly, if we flip it on its head, this engineering question can also be used to understand basic biological questions. So for example, if there's a sensor network in a biological organism, we'd like to understand why those sensors are there, how they were placed there, and what task they might be solving. And so in this way, we can do a hypothesis-driven approach to make the optimization, make a hypothesis of what the decision the animal is making might be, posit that there may be a fixed budget of sensors, and then back out where the sensors might be and compare that to where the animal sensors are actually, where these sensory organs actually are placed. And so to understand our perspective of where we're coming from this, I'm actually going to take a giant step back and talk for a little while about images. Now, this may seem like a stretch for now because we're not interested in images per se. But images are a really convenient way of explaining this perspective because we're very visual creatures and we like looking at images. And so I'm going to show you some pictures to build some intuition about the ideas that will become the algorithm that we're going to be calling SPOC. So looking at images, we make this fundamental observation that the images that your smartphone can take a picture of walking around the world are compressible. They're very compressible. And this is great because it saves us a lot of space on our smartphones. So you can take an image, transform it into an alternate basis. In this particular case, I'm showing its Fourier transform. And you make the observation that in this alternate basis, the data has a lot of zeros in it. And this is exactly the same data. So what we can do is say, well, I can throw all of the zeros away, keep only the top 10% of the data, then do the inverse Fourier transform, and I can get a picture back that's almost exactly what it used to be. Right? So this is just a statement that images are compressible because they're sparse in some alternate bases of representation. So I'm going to say that in a slightly different way by thinking about all of the possible images that this image could have been, except what it actually is. Right? So here's image space. And image space, you may or may not have heard somebody say this at some point, the image space is vast. It's unimaginably huge. Exactly how big it is a little hard to fathom. And so instead of talking about all of image space, I'm going to be talking about a very small image space. So instead of looking at all of image space, let's now think about this image space, which is only 20 pixels by 20 pixels, relatively small. Furthermore, I'm going to restrict it so that each of these pixels can only take on one of two values. It's either black or white. So it's a binary 20 by 20 pixel image. Now the question then is, how many images of this kind can there possibly be? How many different ones can you possibly generate? Now the answer is 2 to the power of 20 times 20. So it's 2 times 4, 2 to the power of 400. And that turns out to be approximately 10 to the 120 possible black and white pictures of the size. Now, this is a very, very large number. To give you an idea of how large this number is, I will tell you that there's only 10 to the 80th number of atoms in the known universe. And this is only a really tiny little image. It's only 20 pixels by 20 pixels. What can you even do with that, right? You can kind of draw a smiley face, right? That's pretty much all you can do. And you can kind of imagine in your head how much this must scale if we're talking about larger and larger images, megapixel images, color images, images that have more channels, videos. This gets really, really huge, really, really fast, right? And so the observation here is the vast majority of these images that exist in this image space, this pixel space, don't mean anything at all. They're just white noise. We don't care about them whatsoever. What we really care about in this astronomically large image space is a very, very small portion that actually corresponds to the natural image space. All of the images that you would actually ever see walking around in the real world, all the signals you actually care about, even though they are complicated, are actually representable by relatively simple patterns. And so this is another way of saying the same thing, that these images, because we could represent them by relatively simple patterns that we can characterize, they are compressible in that way. So back to image compression, right? So now we've said this in several different ways. Images are compressible because you could represent them in this different basis. We can represent them sparsely in this other basis if we know what it is. And this is wonderful, right? We do this all the time, and it is one of the enabling observations of a lot of modern technology and communication. Now, what compressed sensing says is the following. Well, this is great. This works really well. We like image compression, but really, are we wasting all of those pixels, right? I'm taking all of these pixels, and I'm going to throw 90% of them away. So I'm only really taking 1 in 10 pixels is really, all that's important. Why do I have to do that? What if I can get away with only taking 10% of the measurements in the first place, right? So that's the basic idea that differentiates compressed sensing from compression, is instead of acquiring all the information up front, I'm only going to acquire a small portion, a subset of the images to begin with. And so these measurements are subject to some very specific constraints. And there's a well-developed literature around what those constraints are, how do you know you have them, et cetera, for various types of signals, including images, but also other types of things. So once you've acquired these 10% random measurements, there exists an algorithm where you can then computationally reconstruct what the image would have looked like that is most consistent with the measurements I've taken, even though I've only taken a fraction of the original pixels that would have been in the image. So that's compressed sensing, okay? So what I'm going to do now is tell you a little bit more about why compressed sensing works. And this is an image that I have taken from a review article written by Brunton in a IEEE magazine, and it really clearly illustrates how this works in a pretty intuitive way. So what I'm going to say here is X is my image. Here's my picture, right? And my picture is sparse in Fourier space. So another way of saying that is that if I took X as the product of my basis vectors, psi here, and the coefficients will end up being this vector S, and I know that S is full of zeros, and it only has k elements, in other cases k sparse, that are not zero. So I have a k sparse image X in this psi matrix here, in this matrix basis. Now, instead of measuring all of X pixel by pixel, or even basis by basis, what I'm going to do is I'm going to measure it by this measurement matrix here that I'm going to call phi. Okay? I know what phi is. I determine what phi is. I tell the camera what to acquire, so I know what phi is. And after I acquire these images by phi, I end up with a handful of measurements called y, and these are my measurements. Now, there's only m of these measurements, where m is smaller than n. This is important, right? So I've gotten away with taking less measurements than there had been pixels in the image to begin with. Now, what we can do is take track of what we got. We have y, we know phi because I measured it. We know psi because that's just Fourier basis. The only thing we don't know is this vector S here, right? So this turns into a linear algebra problem of a relatively straightforward kind, where we can say that I know y, I can multiply phi by psi to get theta, this theta matrix over here, right? And the only thing I don't know is S. So I can solve this linear system of equations, y equals theta times S, and there's an infinitude of solutions of S that would satisfy this equation. But I don't want just any solution. I want the solution that has as many elements of S as zero, exactly zero as possible. In other words, I want S to be as sparse as possible. And I may not know exactly what K is. I don't know how many elements of S will end up being non-zero. So that's something I have to solve for, right? This sounds good, but it turns out that this is a combinatorial problem. And we don't like combinatorial problems because they're computationally intractable. It can take a very, very long time to solve them because you just have to try all the possibilities. And if S ends up being very, very big, then it becomes a beast of a problem to be able to solve. So what compressed sensing says is, instead of solving that problem, what I'm going to do is solve that system of equations over there, y equals theta S, with the constraint that I want the L1 norm of S to be as small as possible. Now the L1 norm is the following. It's relatively simple. What I'm going to do is take every element of S, take its absolute value, and add it all together. That's it, right? You take the vector S, take its absolute value, and sum all of it. That's the L1 norm of S. Now, the good thing about this particular way of solving the compressed sensing problem is that there's a lot of mathematical theory proving that if you minimize the L1 norm of S while satisfying the equation constraint down there, you will almost certainly end up with the sparsest possible solution for S. And this is great because this algorithm is now amenable to complex optimization that you can solve by your favorite complex optimization algorithm, and is no longer computationally intractable and is no longer something that will take a very, very, very long time to solve, especially for larger and larger problems. So to give you a little bit of intuition about why this works, why it is that minimizing the L1 norm is the correct thing to do here, I'm just going to draw you a little picture. And instead of doing this in very high dimensional space, which I have trouble picturing, we're just going to go down to 2 space, because I can draw a picture in 2 dimensions. So let's say we're in 2 dimensions, right? So we have 2 measurements, the horizontal axis and the vertical axis. What we can do is compare and contrast the normal norm that is typically minimized in something like a regular regression of the generic kind. And what we're minimizing there is usually something called the root mean square error. You take the absolute value of every element, square it, sum it together, and take its square root, right? That's the root mean square error. And so if you look at all the points in this 2-dimensional space that have the same L2 error, it turns out it looks like a circle. Those are all the points that have the same Euclidean distance from the origin. In contrast, if you look at the L1 norm, all the points that have the same L1 norm don't look like that. They don't look like a circle. They look like a diamond. And this pointy shape is going to come into really handy when we're trying to gain some intuition for why minimizing L1 norms promotes sparsity. So specifically, let's think of the problem we were going to solve in the previous page as the following. It's a theta times x equals y problem, right? Where x is the unknown. We know theta, we know y. And so the solutions for x lies on this line here. These are all possible solutions for this system of equations. And so we're minimizing the L2 norm. Really what we're looking for in a very geometric kind of way is the intersection of this line with the smallest possible circle. In this case, this point is right here in red. It has this value on the horizontal axis and this value on the vertical axis. In contrast, if we solve the same problem, looking for the intersection of the line with the smallest possible diamond, instead of intersecting this shape in some spot on the axes, because the shape is pointy, because the diamond is pointy, the intersection is very, very likely to be along one of the axes. So in other words, in this case, the solution ends up being exactly 0 on the horizontal measurement and something that's not 0 on the vertical measurement. And this is very, very likely to happen because of the shape of this L1 norm in 2 space. Now, you can generalize in your head if you try to higher and higher dimensional spaces. Now, these shapes become higher dimensional, harder to picture, but I think the intuition carries. And so we're going to be using this observation, the minimizing the L1 norm promotes sparsity in this very nice way. And what we can do now is go back to image space and think about natural image space again, right? So this observation that image space, natural image space, is compressible and is sparse in appropriate bases is very useful. But we're going to take one step further and look at a more restricted set of problems. Let's say that instead of looking at the richness of natural image space, all the tornadoes, all the trees, all of the animal and puppies you can look at, what if I just give you a very restricted set of images, and I'm going to tell you it's either going to be a cat or a dog. We know this because it's a restricted problem we're trying to solve. Furthermore, I tell you, I don't really care which kind of dog it is. I don't care which dog it is. I don't care what kind of dog it is. It might be a husky, it might be a Malamute. Who cares? All I want to know is it a cat or a dog? Now, this problem is even sparser still than the space of natural images, because the space that separates cats from dogs is potentially much, much lower dimensional than the space of natural images. And this enhanced sparsity is something we're going to exploit in the SPOC algorithm in order to be able to do this discrimination between cats and dogs in a very, very efficient way. So generically speaking, if you want to reconstruct a natural image using compressed sensing, you are probably using somewhere around 10–30% of the pixels of the original image, which is great savings. What we're saying is that if all you wanted to know was classification, no reconstruction, don't care what the cat looks like, you can get away with orders of magnitude fewer sensors still. So if your pixel space were thousands or tens or hundreds of thousands, you can potentially get away with a few dozen sensors to be able to solve a categorical problem of this kind. So how does this work? So to explain how this works, I'm going to show you a very textbook way of doing the image classification problem if you had access to full pixel information. So here's a collection of cats in my training set, a collection of dogs in my training set. And if I wanted to systematically distinguish between cats and dogs and train a classifier to be able to distinguish them, here's a pipeline I might be able to use. And it's relatively simple. So I take every pixel I have, all the pixels in here, and I'm going to turn each pixel into a measurement. So each one pixel 1 is x1, pixel 2 is x2, et cetera, all the way up to pixels x sub n, where n is the number of pixels. In this case, these images have 4,000 some pixels. Now, that's too many. I don't want to do classification in 4,000 dimensional space, so I'm going to run something like a principal components analysis to extract the features from this data set. So now, instead of being in 4,000 dimensional space, we might be down to, let's say, 10 dimensional space, feature space over here. Now, in this feature space, we can then run another classifier, something like a linear discriminant analysis, or LDA, in order to project the data onto this W vector that is fine-tuned to best distinguish the cats from the dogs, the green dots from the yellow dogs, from the green dots from the yellow dots. And so when we look at classification, what you end up with is a projection of my pixel data onto a single number over here. And I can draw a threshold in the middle, and I say everything to the left is a cat, everything to the right is a dog. And I can do this if you give me a new image. Okay? So what that looks like for a new image is, here's my U image. This is my dog Mort. And you take a picture of Mort, which is not in the data set, and we do exactly the same procedure as we had done to the training set. We take the full measurement, we project into feature space, we project that into classification space, draw the threshold, and I can tell you whether or not I think this picture is of a cat or a dog. Now, this is using full pixel information. What we like to do is, instead of being in this full measurement row, we like to be in this bottom row over here, which has many, many fewer measurements that are required to accomplish exactly the same task. Instead of measuring from all the pixels, here I'm showing you a schematic of measuring from, I think it was 20 pixels down here. So all I have to do is measure from these 20 pixels, get the pixel values of them, and I can go directly from the sparsely sampled measurement space all the way down to classification space, and do almost as well, as I'll show you. And what I'm looking at in this middle row here is an illustration of the observation that sometimes you don't have access to full state data. Sometimes you don't have all the pixels in your image, but you only have some random subset of them. So here I'm showing you a schematic of if you had started with a random 10% of the pixels in your training set. So you never had the other 90% of the pixels to begin with. You can do a very, very similar procedure to then also drop down to sparsely sensed measurement space and accomplish the same categorical task. And so this algorithm is, even though I've been illustrating it on cats and dogs because they're intuitive, is not really specific to images. And so the first thing I'm going to show you is how we're going to solve for these sparse sensors. And then I'm going to show you a set of examples on which we've applied this algorithm. So let's continue with the cats and dogs example for a little while. What I'm showing you now in black is the discriminant space that best separates the cats from the dogs. And I'm showing it to you in two different ways. In this left panel over here, we're looking at the black line. So this is in pixel space, right? So there's 4,000 some pixels. This is the thing. The black line is the space I want to pay attention to if I wanted to separate cats from dogs if I had full pixel information. And I can represent exactly the same information over here by resizing the black line in the size of my picture and plotting it as a heat map instead. And you can see that it starts to resemble a face because my training set is composed of faces of various types of pets. Now what we can do is then solve the optimization that's detailed here. So we're going to solve the optimization with a constraint. We're going to solve for S, where S is the same size as my image, such that if you project S using the feature space, it goes as well as possible into the discriminant space, W. And we're going to do so by adding the additional constraint that I want the L1 norm of S to be as small as it could possibly be. So you end up with a vector S, something like this, except much larger, where it's mostly zeros. And there's only very few elements of S that are not zero, and those are the pixels I want to pay attention to. So here what I'm doing is plotting the S for this particular problem, the cat-dog problem, on top of the discriminant vector. And you can see that it is indeed full of zeros. There's only 20 places, 20 pixels, where they're not zero. I pick those places, And I use those as my sensor locations. And you can see those plotted on top in the resized way. And they correspond to relatively intuitive features, visual features of the images. So if you want to tell apart a face of a cat from the face of a dog, you might want to pay attention to the eyes, the forehead, the button nose, and a little bit on the top of the ears, because most cats have pointy ears and some dogs don't. So that might be a distinguishing place you want to look. And this popped out in a completely unsupervised way. This algorithm knows nothing about cats and dogs. It doesn't even know anything about images. All it knows is those fed pixel data, and it was given a labeled set of which ones belong to the category cats and which ones belong to the category of dogs. That's all it knows, right? So this is pretty general. It has nothing to do with images, right? So one of the examples we demonstrate is by showing it to do a dynamic regime classification in the cubic quintic Landau equation. So this equation has a couple of parameter regimes that have qualitatively different behaviors. So what I'm showing you here are two regimes. Here is space, here's time. These are the solutions, or at least the absolute value of the solutions. And you can see these two regimes, they're visually pretty different, right? So this is a straightforward discrimination. So one of them has one lobe, the other one has sort of this triphasic lobe thingy here. And what you can see is that the SPOC algorithm shows you solutions for sensor locations that are pretty sensible. Here I gave it a constraint that I only want 2 sensors. That's my budget, that's all I can afford. And it tells me that I should put one of them right in the middle where I can monitor whether or not there's this tall lobe here or one of these shorter ones here. And I should put the other one on one of the side lobes to detect the presence of one of these side lobes. The problem, this particular problem, is completely symmetric, and so the third one sometimes would pop out on the other side of the other side lobe, but the information is pretty redundant, so you don't really need 3. For this particular problem, you basically do perfectly with 2 sensors. And this is not a surprising result. It confirms our intuitions about these dynamic regimes and how you would, in a data-driven way, distinguish between them. So that's great. Now, what if you applied this to the actual data set of cats and dogs? You don't necessarily know how many sensors you really should be choosing. And so we go through this exercise where we can characterize the accuracy of the algorithm as a function as you increase the number of sensors that you use to characterize the system. So what I'm showing you here is a comparison of the accuracy with the error bars, which are standard deviations, of the classification accuracy using the full image, using all the pixels, with various rank truncations in the feature space detection, versus SPOC in cyan, SPOC subsample 10% in magenta. And you can see that those two closely follow the performance of the full image discrimination. It's not quite as good, but it gets really close. And they, importantly, are as good as each other. And so the subsampling didn't really hurt me in terms of classification accuracy with SPOC, with matching numbers of sensors. Now, you could ask, well, what if this is just a really easy problem? And you could have done it by picking a random handful of sensors. And it turns out that's not entirely wrong. If you picked random sensors of the matching number, so for example here, where these are 10 SPOC sensors of various kinds, and here is the performance if you had picked 10 random sensors, 10 random pixels in these images. So random images obviously does better than better than chance, but it does not approach the performance of these specifically hand-picked key sensor locations that are derived from the SPOC algorithm. And you can also use this graph to see that the performance asymptotes after a certain amount. And so if you had access to the graph like this, you could perhaps say, oh, it looks like after here or so, it's not really doing a whole lot better with more sensors. And so if I had to pick a number of sensors to use for this classification problem, around 15 or so might be a good number to pick. Any more than that, I'm not really getting any more out of it. And the economic decision of how much more information I get per sensor starts dropping. And so you can kind of cut it off right here for this particular example. Now, so far what I've shown you is classification when there are 2 classes. What if you had more than 2 classes? So there's a version of the algorithm that handles cases where you are deciding between more than 2 categories. So here I'm going to use this terminology that C is the number of categories, and this algorithm applies when there are more than, when C is greater than 2, so when there's 3 or more categories that we're deciding between. So there's a very similar optimization that is being solved for. You'll see that it resembles the previous version closely. Instead of imposing a strict equality here that the S completely reconstructs W in a precise way, we're relaxing that a tiny bit by saying that the Frobenius norm of the reconstruction of W by S in feature space psi has to be smaller than a certain small number. Now, practically speaking, this is a very small number, so for examples I'm going to show you, this epsilon here is something like 10 to the negative 10. Now, that's the constraint, and the thing that I'm going to minimize is this quantity up here. So I'm going to minimize the S1 norm, the L1 norm of S in this term, and I'm going to minimize something further, okay? Because S now, because C is greater than 2, is no longer a vector. It is a set of vectors. So if, in fact, S is going to have as many columns as C minus 1. So if C equals 5, there's going to be 5 columns of S that are going to be solved for in this equation. And so what I'm going to do is I'm going to encourage my different columns of S to share as much as possible by imposing this constraint here where I'm going to multiply S by a vector of 1s, which is V. V is simply a vector of 1s, so collapsing all of the columns of S onto one column, and then minimizing also the L1 norm of that vector. There's an additional parameter here, which is called lambda, and lambda is sort of a tuning knob, saying the relative weight of reproducing each of those vectors versus trying to share sensors between different columns. And so as an illustration here, I've shown you if this is a schematic of a solution for S, in this particular case, C equals 3, so there's 2 columns of S. These are the elements of S that are not 0. You can see that there's 3 sensors for column 1 and 3 sensors for column 2. Fortunately, it turned out that one of the sensors they share in common. And so what I'm really going to do is end up with 5 sensors for this particular solution for S. And I can do that just by looking for for rows of S that contain at least one non-zero entry. So we're going to use this version of the algorithm to solve a closely related problem to the cat talk problem. And the data set we're using is from the Yale B-Data Faces extended database, which is available here at this website that you can download. And the data set consists of images of people's faces, and they have a large collection of people's faces acquired under different illumination. So there's quite a bit of variability between different images of the same face. So you can see here for one of the example images, some of the images are lit from above, some from below, some from the side, some from the other side. And if the lighting were eccentric enough, you can see that there's certain cases where much of the face is obscured, sometimes completely black, sometimes you can only see the nose, and sometimes you can only see half of the face well and not the other half. And so this data set kind of strikes that balance between very well curated, but at least having some variability so that these are not identical images, but they're pretty well aligned. So the biggest difference is that the lighting conditions are different. And so in different instances of these images, different parts of the faces are occluded. So if we do this for a set of 3 faces, what we can do, first of all, is remember there was a lambda parameter here, right? Which allows me to turn it up. If lambda is larger, then the number of sensors in non-zero rows of S is more highly penalized, which means I'll get less sensors. So as I increase lambda here in log coordinates from 0 to 100, you see that there is a decrease in the number of sensors that pops out of the algorithm, which is good. That's what I expect, right? This gives me some control over how many sensors are being picked by the algorithm. Correspondingly, for each of those cases, I can see that the performance for about just less than 20 pixels here, 20 pixels for discriminating between 3 different people is actually quite good. It averages above 95%. And as I turn lambda up, the number of sensors decreases and the performance suffers a little bit. It does go down, but not by that much. So even at the bottom here, where I'm only picking 10 pixels to sense from those images, it is still performing the classification between 3 different faces at close to 90% accuracy. In contrast, if you had picked random pixels of the matching number, so here is if you had picked 18 pixels, that's what you would get by picking random pixels. Again, random pixels gets you well above chance. However, SPOC gives you that extra little bit of performance by picking the key locations that are optimally placed to make that particular discrimination. So that was for 3 faces. I'm only also going to show you the similar results for discrimination between 4 faces and then 5 faces. The takeaway here is that the trends are consistent. As you turn up Lambda, the number of sensors drops, which does compromise the performance, but in these particular cases, not by all that much. And so you can make an economic decision based on how many sensors you can afford, and then be able to characterize what you are losing in terms of classification accuracy. So that was looking at the Lambda knob, and I'm going to talk a little bit more about what this Lambda knob does and give you a little more intuition about it, right? So when the Lambda knob is 0, we're basically not penalizing rows of S at all. So these are just the largest number of sensors that you can possibly get from this discrimination. So when Lambda equals 0, there's no penalty for number of shared sensors. And so what you get is that as you then slowly turn up the Lambda knob, you can see that there's pairs of sensors that are close together in space that get collapsed onto one sensor. So these two sensors here became that sensor, and these two sensors here became that sensor. And so what's happening is that as you turn the Lambda knob, the algorithm takes neighboring sensors that may contain some of the same information, and that tries to collapse them onto one sensor and uses that one sensor instead. You can see that there's a number of other differences between these two Lambda values. Some of the sensors have remained the same, some of them have disappeared, some of them have popped up. And so there's something more complicated going on here than the simple explanation I just gave you. But the intuition as you turn up Lambda is that you're encouraging sharing between the different columns of S. So we're trying to use as few rows of S as possible in order to do the discrimination. And so we can also look at the ensemble of sensor locations that are being picked out to discriminate between these three faces. And so what I'm showing you here is a couple of hundred random iterations of 3 different faces of, a random subset of 3 from the database. And what we're then going to do is plot the probability density of where those faces lie in the picture. And so what you can see is that if you run it over and over and over, you start getting hot spots in white and cool spots in black, where the sensors most likely pop up. And here is where they mostly pop up. Now remember, just like in the cat and dog case, this algorithm knows nothing about people, knows nothing about faces, and knows nothing about images. It doesn't even know that these pixels are spatially adjacent to each other in an explicit way. But here's what happens. It picks out these locations. It picks out that if you were trying to tell people apart, you would look at their eyes, you would look at their nose, you would look at their nostrils, and maybe you would look at the corners of their mouths. Those are the places we want to look at. And this makes a lot of sense because it resembles exactly what humans look like when viewing a face for the first time. So what your eyes are doing right now as you're staring at this image of a human face is you're doing something like the following. If I could track where your eyes are looking, you would be looking between the eyes, you would look at the mouth and the nose, and go back and look at the eyes and the mouth again, and then you would maybe look at the face and then go back right to the eyes. Right? So most humans, when viewing another human face, spend approximately 90% of the time looking in this triangle between the two eyes and the mouth. And that is remarkably consistent with what we're finding with SPOC, again, with no knowledge of what humans do or what images are. These are just the places that are the most different between the 3 different faces that we've trained it to do. And this is not a surprising result. In fact, it's something that we've known for a very long time. But it sort of gives you a little bit more intuition, and it gives us some confidence that this algorithm isn't just doing random stuff. It's actually picking points in the images that are actually important. And it's important to give that intuition because when we start applying it to data sets for which we have no visual intuition, we want to be able to say and have some confidence that these are indeed sensors that are being picked out. That kind of makes sense, right? It's picking out the most salient features in the data set. So when we apply the SPOC algorithm to a totally different kind of data set, here what we're looking at is a set of gene microarrays for some 83 samples of different kinds of cancers. This data set is available from the website down below that you can download. And the data set consists of 83 samples of 4 different types of cancer that had been diagnosed by physicians by biopsy. And what they've done is that they've done a gene microarray on some 6,000 genes. And so here is just a heat map of the data set, the full data set. It is a matrix of 6367 by 83, where each element corresponds to the gene expression level of that gene in that particular sample that has been classified into one of these 4 categories. So C equals 4 in this particular case. Now, what we would like to do is say, well, which of these genes is actually important? Look at this. It's a little hard to tell, right? There's a lot of them. It's very confusing. And so there's a variety of different ways to do this feature extraction, this feature selection. And if you apply the SPOC algorithm, here are the genes that pop out. We get 28 genes that do very, very well in terms of classifying between these 4 different kinds of cancers. These are their gene numbers. Doesn't matter in particular what they are. They can be looked up. And what you can see is that now we're picking out classical classifications that are based on pretty visually saliently different aspects of the profiles of gene expression of these 4 types of cancers. You can see that this first type kind of has high expression here, but not for the others. This type of cancer is sort of characterized by high expression of this set of cluster of genes right here. This one is characterized by high expression of this cluster of genes, and this one is pretty uniquely high in this cluster of genes right here. And so this gives us a way of not only picking out the important features in this data set, the important genes that are probably most determining the differences between these different kinds of cancers, but it also gives us a way of designing diagnostic tools. You can think of this in terms of if you could only afford a very, very small gene microarray chip, which genes should you be putting on that chip, right? Here is one potential answer for doing that. You can also think of this in a very abstract context. So far we've talked about physical measurements, biological measurements. You can also think of this in terms of abstract types of measurements like a questionnaire. If you had a really long questionnaire that you can use to ask people certain types of questions and to determine something about the respondents, but then you only had 5 minutes and you can only ask 5 questions. Which 5 questions should you ask? So there's a lot of these types of questions, these economical decisions that need to be made in terms of if you only had a fixed budget of sensors, where should they be placed to best inform a very particular task? There's no free lunch. This thing only does that one task, right? There's no reconstruction, and it does not generalize unless you retrained it to any more different categorical tasks. But if you're in a scenario where that's something you would like to optimize, then this is one framework for doing that type of optimization. And a little bit of future work, we're considering expanding the framework to explicitly take into account the fact that sometimes different sensors have different costs. For example, if you're putting buoys in the ocean, it is easier to get to locations that are closer to a shore, certain shores, than somewhere out in the middle of the ocean. And so those 2 sensors may have different economic cost. And so that can be put explicitly into the cost optimization. Another possible extension, for example, is extending this framework to take into account hierarchical decisions that can be made. So, for example, you can first tell whether or not it's a pet or a human, and then afterwards whether or not it's a cat or a dog if it happens to be a pet, or what kind of human, which particular human it is if it happens to be a human. And so, again, there's this joint optimization where you want to be acquiring as few measurements as possible in order to inform the structure of the decision making. All of this is based on having really good training data, but once you've trained up the algorithm, it can perform these categorical tasks with remarkable efficiency using very, very few sensors, especially point sensors, where each point sensor has some fixed cost you're able to articulate. So there's a lot of code that's associated with this work that is available at GitHub that you can download. And it also has a couple of examples that are fully worked through so that you can follow along at your own pace and have fun. Thanks.